So my name is William Elmer. I go by Will. I'm here representing Lawrence Livermore National Laboratory and the work that we've done with Procter & Gamble. I wanted to start off with some comments I heard over at lunch. People were asking, what is supercomputing? I'm more of a user of supercomputing. I sit in the Defense Systems Analysis group, and so I do a lot of analysis of conventional munitions. And I tend to think of supercomputing as the point where communication becomes ineffective. Additional communication becomes ineffective. So a lot of people see this like in explicit dynamic analyses, like some of the ones you'll see today. You will overwhelm the communication of the machine by trying to parallelize too far. So that's what supercomputing means to me. And if you think about that from a broader paradigm of a lot of different problems that people solve that aren't just structural engineering mechanics, that could be something where communication is taking place on a cell phone. And communication is very important to the end user. There could be other problems at the other end of that spectrum which are very data intensive, and so you get a long way into processing the data before communication starts to become too much of a burden for the objectives that you're getting to. So we'll see some of that. So today I'm here to talk about paper fiber products, and this is always interesting, sort of a wink wink, nudge nudge. But one thing that Lori mentioned was that paper drying, but that's accomplished by material compaction, so going through a roller and getting more water out that way is worth about 80 trillion BTUs to the entire US economy. We could actually lower the energy usage that way. Those are for paper products that you write on. The paper products that you interface with your hands are done in a little bit different way. So they're not heavily compacted into that sheet of paper that's very slick, right? We want to make sure that we have a certain level of customer satisfaction that's involved with these products. And so the Department of Energy actually did this bandwidth study that showed there's 147 trillion BTUs of potential energy savings in R&D. So these are a little bit more far out applications of research and development that can lead to better performing products that can be made at a lower level of energy during the drying stage or during shipping and transportation if they weigh less. And the key here, though, is that the stakeholders that we're working with, the folks at Procter & Gamble, have to maintain that customer satisfaction. So we have this bear here. This is the Charmin bear, and he's representing the happy customer throughout this process. So the DOE has equivalent needs, or we have similar needs. We know that innovation in our processes and our products lead to growth, right? We don't have the same sort of ways of measuring that innovation or getting the sort of the bang for your buck. But we do know that the product development that we're doing has to share time with the production that we accomplish. And for us, we're stewards of the national stockpile. And so we have to make sure that we, are maintaining the safety and reliability of that stockpile. And we take, we spend a lot of our research dollars on national resources at the supercomputing level. So how do you manage these constraints on those products while also innovating, right? So again, this is something that both industry and the DOE finds as a challenge. And we get to take these national resources and do something like simulating paper fiber products right here. So this is one example of that. What we were able to achieve through this work was the most paper fibers in a single simulation. And these are a particular morphology of paper fibers. They actually have some curves in them. And the way that we address that that hurdle technically is a lot of what this presentation is about. But as you can see here, we have a very well represented paper towel. And I put this image on a poster for the AMO meeting. Somebody came up to it and it was very high resolution and said, "Is this a electron microscope image?" So it was a good indication that we're headed in the right direction in terms of representing these things. So Procter & Gamble is a very well versed user of HPC. They have on-site HPC. A lot of their business units use HPC. They have a global engineering unit that sort of sits over those business units and comes to provide services to those business units. And the fiber scale for them is the first step in a very critical hierarchy. They have to start basically designing this paper product with a mixture of fiber weights. So they have some larger fibers, they have some smaller fibers, they pour those together into a vat, and then they run that through a roller in real life. Now, in computational geometry, what you're doing is going from the fiber weights to a set of computational geometry representations of those fibers, and then you have to mesh those fibers, and you have to perform what's called a consolidation simulation. And the reason why you have to do the consolidation is because the software that produces the geometry for the fibers does not know anything about physics. It has no way of enforcing contact between the fibers. And so in order to get around that constraint, it puts these fibers in a very diffuse through thickness configuration. So you start off with a very thick, diffuse mat of fibers. And what you have to do is use physics to consolidate that on down. Okay, so what we're doing is we're focusing our effort in this project here on the meshing and the fiber consolidation simulation. However, in order to be effective in doing virtual prototypes and computer-aided engineering for their paper products, Procter & Gamble is going to need to take that consolidation simulation and then imprint their proprietary business-sensitive designs onto it. And they have an entire pilot line of manufacturing capability where they actually do this in real life. That's a very expensive thing to run. So what they'd like to be able to do is run these kinds of forming simulations after the consolidation simulation on different product ideas, and then they have to get to product performance. So they have another simulation after that where they're going to need to poke and prod and establish potentially constitutive behavior for the paper products, not only for the way that the customer experiences those products, but also for the manufacturability. They want to make sure that their paper doesn't actually come off the line as they're manufacturing it. And when we were there for our visit, we're doing the outbrief here, we actually saw that line sort of come to a halt, right, as the paper pulled its way through, broke at some point, and then they had to send 4 or 5 guys out there to fix that situation. If that happens at a production facility, it causes a major delay. So again, we have a very limited focus here, and one thing I would say about this project is that the PIs are paired up with the company at the conceptual project development phase. And this is where the listening really has to happen. You have to listen to what problems and issues the customer has, in this case Procter & Gamble, and come up with a reasonable statement of work that you feel confident you're able to execute, but that also might be limited to a subsection of their larger problem. So here's the results of our collaboration. I already showed the simulation that we had for 15,000 fibers. The truly outstanding result here is that we produced a piece of software that we call P-Fiber. P-Fiber was focused on the pre-processing task of generating the mesh for these problems. We were able to reduce that meshing time from 19 hours, and those are our numbers. We didn't use any of the techniques that Procter & Gamble actually uses to mesh these fibers, but if we were to run our code in serial, it would take 19 hours. And when we ran it in parallel on 1028 cores, we got that time down to 5 minutes. So the other thing we're able to do is mesh larger and larger representative domains of paper in an equivalent time. So that's weak scaling. And this is a really unique opportunity for weak scaling, because if you think about it, in order to increase the number of elements in your problem, all you're doing is just simulating a larger and larger domain. Not a lot of companies have that luxury. For example, auto manufacturers, if they're doing a car crash simulation, they're not just crashing 4 cars into each other or 10 cars into each other in order to get the weak scaling behavior. What they want to be able to do is have more representative finite elements, but to do that in an explicit simulation, it means your time step drops, and so you are sort of limited if you want to do a run overnight. But again, very unique opportunity to show weak scaling, and we were able to show that we can keep their meshing time constant as the problem size grows. So how do we do this? One thing that we do is we use the API to a meshing software called Qubit. So Qubit is a Sandia software. It has a Python API, and what you can do is actually load that Python module and then initialize the C++ meshing engine without starting the graphical user interface. And it's sort of like an Easter egg almost. But it is a way that you can leverage the power of running many, many instances of Qubit and controlling those instances and sharing information using the message passing interfaces that are in PyMPI. And so we get this, the mesh of these fibers in many different containers, right? So for this, I've chosen the analogy of a bowl. The bowl contains many, many grains. In that case, those are the fibers. And what we need to do first is we need to take multiple files and we need to dump all of those fibers, in that case, or grains, out onto the table. So we first open multiple SAT files. We can do one node per SAT file. We can do many processes opening the same SAT file, and then only a portion of that bowl to dump out onto the table. But we have a parallel process for opening the SAT files, and memory will constrain that. We can't have an unlimited number of processes opening the same file, or else we'll run out of memory. But we can deal those now grains out into individual files on the file system. And so we have as many files on the file system as there are fibers in the simulation. Then the real fun starts, because once we have all those fibers set out on the table, we have perfect parallelism. And we can open up an instance of Qubit for every single fiber that is on that file system. We didn't go to that level of scaling, but as I said, we used about 10,000, or we used about 1,000 cores for 15,000 fibers. So they didn't have very long lists of fibers that they had to iterate through. These are Stl representations, so stereolithography representations. They sort of look like these bacon strips. I'll show you an image on the next slide. And so the mesh had to get cleaned up, or the geometric entity had to get cleaned up. That's step 3. And then the mesh was created. These are all hexahedral meshes. The software is capable of writing either thick shells or solid elements. And it will also check for deficiencies in the mesh as it creates the mesh, and it'll fall back to a routine that Qubit has put out recently called sculpting, which saves some of those errors. Even though there are fallback options, there's still a few fibers that get meshed with deficient geometry, so we'll actually check for that. And then we'll write the node and element files to a bunch of different files again, as many node and element files as there are fibers, and we'll then combine those lists of files in an include statement for the Paradigm run. So after meshing, this is what Paradigm looks like. This is the high fidelity physics that we're all used to. And one thing that you can see is that there's not a lot happening in the simulation until the very end. These collections of fibers are so diffuse in the through thickness direction. And this is actually from a simulation that only contained 1,000 fibers. So it had a much more diffuse network of overlaps of the fibers. But not much occurs until the fiber reaches its consolidated value. And that actually has very interesting implications on the scaling behavior of the problem, and it makes the scaling behavior very, very hard to analyze or to get apples to apples comparisons on. So as I said, pFiber, this software that we created, exploits a number of features in Paradigm and Visit. It creates an input deck for Paradigm. It creates a batch submission file for Paradigm. And it also facilitates the motion of data back and forth from the machines which are a little bit higher clock speed, one of which we call Sera, to more massively parallel machines with very particular architecture, one of which is called Vulkan. So you'll see some scaling results from that. But it facilitates that data transfer because they have actually different file systems. and tries to make it easy on the user to move the data around. And then I mentioned this last option where it creates this rogues gallery of fibers that it wasn't able to mesh correctly, but it's checking for those rogues in parallel once again. So there's a very limited list of fibers that you have to run through on any given process. One of the things we set out to do initially from the start of this project was to make sure that this tool would be capable of transition to industry. And again, this is something that I think is very important for this HPC for manufacturing project. But it is mobile. We built this with setup tools. It uses Python, Py4MPI. These are obviously open source and free. Qubit and Trellis is a proprietary license. Trellis is the brand name for that. Visit, which is licensed by LLNL under the BSD license. As Laurie mentioned, the licenses that come out of CRADAs and HPC for manufacturing include negotiability terms for any IP that's produced by the lab partner. And again, we don't modify any of these additional things, so we don't trigger any GPL clauses or anything like that. One of the things we knew we wanted to do from the beginning of the project was run on Vulkan. And one of the things Laurie asked me to highlight was what was the benefit to DOE. Before this project, nobody had really used Paradigm in anger on Vulkan. And so we were able to run our biggest consolidation simulation, 20 million elements, 15,000 fibers. There was a larger run on NCSA Blue Waters with LS Dyna. And so we weren't able to do that size of a simulation, but we did run to about 10,000 cores, and we were short of the NCSA Blue Waters result by, I think, about 4,000 cores. So we're getting there, 60% of the way or so. We also used a lot of the Sera machine, which is a higher clock speed. It's interesting because there's sometimes not a lot of users there, so we were actually able to use about 10% of that machine for a couple of weeks in May when we were cranking things out, and that was about 80,000 CPU hours. The entire project was about 7.7 million CPU hours. We also compiled Paradigm on Vulkan. The developers there added a couple of speed improvements, including input-output. So Paradigm can now write a binary mesh and element file, and then the individual task will just go and read the node and element information, which is particular to its task, and not have to read the entire ASCII file from the disk. Again, what I was saying about supercomputing being the sort of limit of your problem, your very specific problem domain, to when communication begins to overwhelm it. That's what you're seeing here. So these are a variety of different sized problems. The ones that run the fastest, and here higher is faster, are the smaller size problems. So we did problems in the 3 to 4 million zone range, 7 million to 11 and 14. And so as you go down this way, you see the peak is moving slightly to the right, which means that it needs more and more cores to break down the scaling relationship. But there were some issues with throwing a bunch of cores at the larger jobs that we're still working with the Paradigm developers on. And so what we're seeing here is both weak scaling and strong scaling studies. And you can see that we haven't quite maxed out on the weak scaling yet just because of a couple of technical hurdles. And then I would say that on a back of the envelope calculation, we had this simulation of about a square centimeter of paper fiber product. They'd like to be able to do to 10 square centimeters. That would be possible with Vulkan, but it would take the entire machine. So I think that's a little over 300,000 cores. We also did scaling on Sera. And if you see the image here on the left, this is the only time that the problems were actually run all the way to completion. So one thing about these problems is that the time taken in Lagrange contact tends to overwhelm the problem as consolidation takes place. And we were applying fixed boundary conditions from a displacement standpoint. So we were able to generate arbitrarily large through thickness stresses that would sort of compete with the calculation of the Lagrange forces to get the nodes out of the elements on each time step. And so what we would find really more of is the calculation sort of grinding to a halt as we tried to compress this thing to unrealistic through thickness stresses. So again, those scaling results that you saw previously are just 1 or 2 time steps. Actually, I shouldn't say that. They're 16-hour jobs, but the jobs went as far as they went. The results here are actually getting all the way through consolidation, but you can see that the problem size is significantly smaller, only 500,000 zones. So to wrap this up, computers are always getting more powerful. We know that. But pre-processing is not necessarily given the attention that it deserves. One of the things that we were able to do here is speed up by a factor of 2, a very simple problem with 100 fibers, speed up by a factor of 6, a more complicated problem. You're seeing those scaling results with p-fiber here. And then for that really hairy problem, which you're seeing in the blue and red, 15,000 fibers, we had a 225x speed up. So again, you can always now design a problem that you cannot even pre-process, let alone run through the physics solvers in any kind of efficient way. And so if you're going to be able to do these ensemble runs, if you want to be able to do computer-aided engineering, which has simulation in the loop, you have to reduce the pre-processing time. And that's something that we were able to accomplish for the sponsor on this particular activity. So with that, I'll take any questions.